So, good morning. Let's just review the situation. First of all, we're considering domains D. In the complex plane. And we have a standard orientation, so the orientation of the boundary looks like this. So standard orientation. Of the boundary. With respect to the standard orientation of the complex plane, pair 1 and I. And we have Z running around in the boundary, and we have a point zeta inside, and we take a point Z0 so that the disk, let's say, it's not a very good picture, I'm sorry. Let's call this radius of this disk lies in the domain. So this disk is radius R about Z0 is in the domain. And in fact, its closure is in the domain, so that we have its boundary in the domain, and it has the standard orientation. So the disk of radius R about Z0, which contains the point zeta, has standard orientation. But it's important that its orientation is such that it's a boundary of, as a boundary component of the difference of D minus the disk. So that's the fact. That's this picture that if you run around this way, the usual, you keep the domain on the left, and it's the same statement here. So that's the fact. Okay, that's the setup. And that's the setup. And then we consider F holomorphic in a neighborhood of the closure of D, so that it's regular on the boundary. In particular, smooth. We now have used this fact that we proved last time, Broussard. This is the proof of Broussard's puzzle, prove that it's smooth. And as a result, you can compute f of zeta as the integral using the Cauchy kernel around the boundary of D of f of z, z minus zeta dz. The remark is, originally, Broussard did this for rectangles. Thanks. And this proves that F is smooth. And therefore, the general result, which is called the Cauchy integral theorem, can be, to prove it, we may apply Green's theorem. Oh, God, let me write that carefully. Are allowed to apply Green's theorem and this proves the general result. Which we use in this case is the integral around the boundary of D minus the disk of F of Z minus Z of dz is 0. And this is the Cauchy integral theorem. Okay, you can forget all of that, and here's the formula. Okay. So, in some sense, this is very deep because we need Stokes' theorem, and we need a little bit of thought on the regularity and so on. And what we do is this is around we have this thing here that we can, this disk, and we can use that, so we write this as F of zeta. Let me just write it all here, 1 over 2 pi I. Here we go around the boundary. F of Z. And then I cheat a little bit and subtract off this Z0, but then I put it back in. Z, just the usual thing to get Z0 involved. And then, of course, let me just do this all out here so to remind you where we are. I pull it out. And then I have a geometric series, 1 minus zeta minus Z0 over Z. Let's put the dz here, minus Z0. And we force this geometric series here so that this distance, zeta minus Z0, divided by Z minus Z0, and that's the important thing. Zeta is inside this disk, so its distance, I don't know where zeta is in this picture. Zeta is in the picture here. This is the distance here. Zeta minus Z0 is very small in comparison to the distance here, Z minus Z0. So we cheat a little bit and force in the geometric series, and that gives everything convergence that I talked about last time. So this thing is a power series. in z to the n, and now we have to figure out what the coefficient is of this. So we expand this in the geometric series, and you will see that an is 1 over 2 pi I integral on the boundary of f of z dz over z minus z0 to the n plus 1. Okay. Now, if you like, as some people do, to start my lectures in the 6th lecture with this is, I think, and define a holomorphic function to be that. That's it. This is all equivalent here, so you can forget it. It's a power. Holomorphic functions are power series locally, and we did all this work using Stokes or Green's theorem, Darboux idea, all sorts of stuff, just to prove it. Yes.
And in the power series, you need a zeta, not z. So it's AM zeta minus Z0.
No, thank you very much. Yeah, because this is a power series in zeta. Yeah, I'll thank you. Right, because we have zeta of that integral and then I expanded it there. Okay, any other questions? That's it. Okay. Fine, so we can start the lecture here and just say holomorphic functions are those which have convergent power series. And you see there's a little bit of, this is a Weierstrass viewpoint. Is this. Let me draw a picture of how Weierstrass thought about this stuff. He says, well, I'm going to draw a bad picture, by the way. So that is D. And it's very possible, we know if we have Z0 here, we have a power series expansion around Z0. And if you have a point Z1 here, say, Z1 here, then you might be incredibly lucky and have a power series expansion that goes outside the domain, and I purposely made it go into the other part of the domain. You get what I'm talking about? So there are little disks running around, and you have a power series expansion here, and a power series expansion here, and a power series expansion here, power series expansion here. That's how Weierstrass thought of these things, just putting together power series expansions. But you could get very excited by doing this. Power series, and then you do this, and you're extremely lucky you actually can go outside the domain and the thing is convergent for some reason. And then you take a power series expansion here, and you go around and you're talking to your girlfriend or boyfriend or whatever it is, and you're going around here, and you're going around here, and you get power series expansion. Wow! You see what I'm saying? So you have a power series expansion around here, and you have a power series expansion around here, and it's not at all clear you get the same power series expansion. Right? Okay. So this is what Weierstrass was talking about. All holomorphic functions are power series expansions, but that's a local thing and you have to put them together globally, the way they piece together. So this is going to play a big role in our discussions. Okay, so our idea is to think at first, the first idea, at first, think in power series. Okay? This is an interesting topic. Power series in one variable. So let's take, it's enough just to consider a special case. Let's consider Z0 equals 0. So we're interested in power series of the form sum A n Z to the n. I know it's boring, but that's it. Just power series in one variable. Okay? And so, here is 0, and we suppose that someplace, we don't know it conversion, we don't know anything, but we just write the thing down. Okay? So let's suppose we don't know anything. Let's suppose we just write it down. A to the n, any sequence. But let's suppose, and we're thinking in terms of radius, we're thinking in terms of convergence on convergence on disks is a question. On some disk is a question. And so you all have very good first year courses and very good courses here, Jacob's mathematics and so on. So we suppose this series converges at a point. At the point, say, z equals a. Just at a point. This is what we talked about in high school. Something converges at a point. Right? This means this converges. A is very bad here. Maybe z equals b. A and b to the n. Okay. Okay. And in fact, let's suppose here that we have, here is a radius here. Let's call this r0. And here is the point B. And B is, let's say, r0 e to the I phi0. Okay, some point on the circle like that. So that means that this thing converges. R0 to the n, e to the I and phi0 converges. Okay. Everybody knows what convergence means. It means that the relevant sequence of numbers converges. The relevant sequence of numbers is the sequence of partial sums. This means that Sm, which is the sum of this guy, An, b to the n, from n, say, equals 0 to n, converges somehow to something S0. That's what that means. That means that thing is a quotient sequence. This sequence is a quotient sequence, so Sm is a quotient. Right? But this implies certainly that An, Bn goes to 0 as n goes to infinity. Right? Because it's quotient. Quotient means that for all epsilon, there exists an n depending on epsilon, such that Sm, Sk minus Sl, let's say, is less than epsilon, given epsilon for k big and L bigger than or equal to this big N. And that means certainly that this term goes to 0, because if it didn't go to 0, you could make these things blow up for arbitrarily big N. Okay, so this thing goes to 0. So let me write it here. B, what is it? B, I'll even write it here. An r0 to the n e to the I n phi 0 goes to 0, so I take absolute value of that thing. This goes to 0, and so that means that An in absolute value times r0 to the n goes to 0. Right? Now, we don't know about An, so you always keep an example in your mind that we don't know too much about absolute value of An. The sequence -1 to the n over n, z to the n, and z0, and b equal 1. I took a bad example. So it's alternating and so on. It converges at that point. So that would be an example where this thing converges. You know, I mean, everybody knows this alternating thing converges. But in fact, this thing does not diverge. So, sum here. So sum of the absolute values does not converge. So right at the boundary, we really don't know what's going to happen, but because you might be lucky, so to speak, but because of this phenomena, you better go a little bit smaller. So that means, at least for r less than r0, I'm going to go a little bit smaller. yeah, sum of absolute A and R0 to the n, R to the n, less than or equal to sum A n R0 to the n over R to the n. Well, so have I done this right? R to the, I want to put in an R0 here. So, no. What do I want to do here? What do we have about this? So let's look at this. This is correct, right? So I have what do we want? Yeah.
I guess we also want to put how about the e to the in phi 0?
Hmm?
Why don't we use the e to the I in phi 0?
Yeah, I don't care about it because I've taken absolute values.
Oh, right.
Okay? So that's the first point. This goes to 0. Okay, so that means that an times 1 to the 1 over n times r, I'm going to do this really slowly here, right? Times r to the n goes to 0, right? Okay. And that means that r to the n I hope I've done this right, 1 over a to the n times r to the n the R0 has to be in this, is R0, right? That should be less than 1. Let's see if that's right. Right? Well, is that really right? Is that really right?
It should be smaller than 1.
Hmm?
It should be strictly smaller than 1. So that
Should be strictly smaller than 1,
so that it can go to 0.
but it could converge to 1 in some sense, right? Right? So if this thing is, you see, this number raised to n power goes to 0. Yeah? But it's still possible that this thing is converging to 1. So it says that this is the case. Lim sup of an 1 over n times this number is less than or equal to 1. Isn't that right? Have you ever thought about this? Maybe not. Have you ever thought about this in your basic analysis stuff? Okay, then it's worth thinking about now. Okay. So just because this thing goes to 0 doesn't mean that this thing goes to 1. Right? This thing, this thing is less than 1, excuse me. Right? It could converge to 1. Right? Yeah. So we know, all we know is that the supremum of these things, it cannot, the lim sup of this thing cannot be bigger than 1, because if it's bigger than 1, then this certainly doesn't go to 0. Because I can pick out a subsequence here where they're all, the lim sup is bigger than, okay, now you've got it, right? And so that says that R is less than or equal to the limb suit to 1 over the limb suit of absolute A n 1 over n. Again, this goes to 0. But because this is everything to the n, you don't know exactly what's happening inside. But this cannot be infinitely often bigger than 1. It cannot be infinitely often bigger than 1, because then we would found this, right? So it said, this is what this says. Okay, look at this. Okay. So, the little lemma that we approved is convergence of this thing, a n b to the n, convergence as above, for b equal r e to the I phi implies what I call it R0. It's a special value. Implies that R0 is less than or equal to R0, yeah, R0 is less than or equal to the limb, 1 over the limb suit. A n to the 1 over n. Okay? Okay? And now, that's a little lemma. And now take R strictly less than R0. Let me emphasize this. Take this less than R0. This says that this thing, a n r to the n, now let's see, is strictly less and not equal. Well, let's put this in here. This is strictly less, so how are we going to do this? Strictly less than a n. Oh, I'm getting these things wrong. So this is strictly less, and well, okay, I'll write down what's obvious here. 0 to the n. So it says that the sum of a n r to the n is equal to the sum of r to the a n r to the n over r0 times r0. This is to the n. Yeah, and now we're okay. Look what we got. This term goes to 0. So this is strictly less than sum r to the n, r0 to the n, and this converges. Okay. Are you mystified? Okay. We're very, first of all, we have this estimate. Second of all, for r less than r0, we have this estimate. Third of all, we know that a n r0 to the n, in fact, even goes to 0. So this sum here, I cheated here, put in Rn, because I can handle that, and a n r0 to the n, in fact, even goes to 0. So this is less than Rn over R0, and this is geometric series. Okay? I see blank faces, so where are you mystified? I hope you're not mystified. I think you're mystified. So let's start again. If this thing really is converging, then R0, you have a bound on R0. Right? That means that R0 has to be less than or equal to this thing. But if R0 is even strictly less, if R is strictly less than R0, okay, then this converges anyway. Okay? So let's see here. If so we have R0 is less than 1 over the lim sup of the nth root of an, and R less than R0 implies uniform convergence. For Z less than R, or even less than or equal to R. Okay. And let's see what happens if R greater than R0, greater than this, what happens? What happens? If R is bigger than R0, okay, here it is. If R0 is bigger than lim sup here, of the nth root of this, where is it? Here. Here. If R0 is bigger than the lim sup of this, that means that this term is infinitely often bigger than 1, and this means that this does not go to 0. Okay? So what does this prove? This proves that this little proposition proves that for the series sum a n z to the n is uniformly convergent for on the disk of radius r about 0 for r strictly less than 1 over this thing, the lim sup, and for r bigger than this, it is divergent. It is not absolutely uniformly convergent. Are you okay with this? Did we talk about this in Analysis 1 lectures? With this exact, so, again, you just need to think if it converges, that means that the terms go to 0. That's clear. And if they go to 0, it means that this goes to 0. And it means that that this thing is less than one. Yeah, is this the point? So this goes to 0. This goes to 0. So could this be, this thing could be 1. Okay, what could happen is this thing could go to 1. This thing could go to 1. And still this be less than 0. Go to 0, right? That's the point. Yeah. So you don't really know what happens on the boundary. Yeah. You don't really know what happens on the boundary. And if you're beyond the boundary, yeah, then you certainly have divergence because this thing is too big. Okay. If you're less than the boundary, then you have uniform convergence. Okay, forget it. So we define the radius of convergence in analysis -1. Of the power series, sum a n z to the n is defined as, I call it rho always, equal 1 over lim sup of a n absolute n. Okay. That number exists no matter what. Lim sup of some numbers exists always. Okay. Okay. That's it. No more discussion. Okay. So then the algebraists in the audience are very happy about this because it means you forget analysis, and which I've forgotten. And it says you should go to what the algebraists would like to call, denote by this. This is the algebra of formal, or ring, sometimes one says, the algebra of formal power series. In the symbol X. So I think computer science don't worry about what is a symbol. But somehow I worry for about 5 minutes at least what is really a symbol. But if you worry about what is a symbol, it's something you can write down, that's it. I mean, it doesn't matter. Okay? And if you don't like this, a formal power series is this. It's just that. And if you don't like that, that's the same thing as an ordered sequence x1, a1, a2, and so on. Okay, so if you really want a definition of it, it's this infinite vector, which you can write down explicitly. But we are thinking of it as a formal power series. We're thinking of it as a power series in a symbol x to the n. Why do we want to do that? Well, the first thing is, given a coordinate z, as I've monkeyed around here with this convergence stuff, given a coordinate z, we have a radius of convergence function, radius, and I'll emphasize, depending on the coordinate z, a convergence function, which is a mapping to the non-zero numbers. That's the first thing. All of this stuff here is just so we can forget it, right? We are dealing with the formal power series, something that's a very simple-minded thing, and we have introduced, based on some idea of convergence here, a thing z. And the notation is, rho, and the notation is a power series convergence converges, whatever that means, if and only if rho is positive. So you have the ring or algebra formal power series. You have a function on that called the radius of convergence. It's just some function. You compute it out. It's not very hard to compute it out. This thing is rho is 1 over rho of a formal power series. Let me write it down. Rho sum a n x to the n. Yeah, of a formal power series. Of course, depending on this coordinate, but that's okay, equals 1 over lim sup. It's a terrible thing. Right? It's a terrible thing.
Excuse me. So the Z, is it the center of the circle on which we want to evaluate the radius of convergence? Or where does the Z come from?
Z is a coordinate. Yeah, let's look at this blackboard. We start with a situation in a complex plane. Z is the linear coordinate. Okay? We talked about power series here. We talked about, well, okay, that's power series in zeta, but I'm talking about the power series in Z the whole time here, the power series in Z.
So it's just the symbol, the same as the X or whatever?
No, but if I change Z, if I use another coordinate, I'm going to change the definition of rho. I mean, you would allow me to have 2Z as a coordinate.
Which is what exactly?
Huh?
What exactly do you mean?
2 times Z.
Yeah, what do you mean by the coordinate?
Okay, yeah, it's a very good discussion, this discussion. Okay? Yeah? I have a point P in the complex plane. First of all, I have no coordinates in that picture whatsoever. Okay? And now I say, well, I make the identification with R2. Yeah? And how do I make that identification? Every point in R2 has an expression with respect as a vector space with respect to this basis. And that means that P can be expressed exactly with respect to this basis as x plus times E1 plus I times E2. Well, no, I'm sorry, x times E1 plus y times E2. Okay. Now I change the basis. I change, instead of using, I could make an incredibly complicated change of basis, and that would give me another way of, and this I send to Z equals x plus I1. Okay, now I change the basis. That's why I said I give you the stupid change of basis. I multiply the basis element by 2. Okay.
But how does it affect rho? Because
look at it. I mean, instead you have a power series. That's a very good question. How does it affect rho? That's the reason I said be sure to write Z, because rho is defined in terms of Z. Well, if I say here sum A and Z to the n, and now as a function, this is going to be sum B and zeta to the n. where zeta is the change of coordinate, where zeta is another coordinate. 2 times z, okay? So if you see, I put this in here, this is in Nico's coordinate, well, I'm saying 2 to the n, z to the n. Now these coefficients are changed by some astronomical thing. Okay, and of course, the limb sup of this guy is the same as the limb sup of this guy, but you can see what happens here. 2 is going to be playing a role. I've doubled the radius of, I think by doing this, I've doubled the radius of convergence. And you can see this, I have a disk and I just double it in terms of what you're looking at. Or I'm not sure, divide it in half. Okay? It depends on the coordinate. Okay? So given a coordinate, I have this radius of convergence function, and the favorite coordinate by algebraic thinking people is the standard linear coordinate on the complex numbers. But I'm an analyst, so I pick any coordinate I like that's convenient. Okay? Okay. So the best thing to do is again, I'll repeat what I just said because it's very simple and yet very complicated. So every homomorphic function has a power series development in something. Depends on the coordinate. Right, when you change coordinates. Right. This thing converges or not, I mean, at some points. If it converges at a point, then you go inside that point a little bit and it converges on that disk. We were talking about the questions you asked. Now we really see how important disks are playing, what the role of disks is playing. Right. Okay, so we went through this horrible discussion of limb sup and all of that, and we figured out in this coordinate z, the radius of convergence is that. And that defines then a function on the algebra of formal power series. Now, why did I say algebra? So, is one a vector space over the complex numbers? You understand what I mean by that? I mean, if you take 2 elements of this thing, you can add them and take linear combinations of it. Well, it's pretty stupid how you do that, right? You have formal power series. Let's do it one time. A sum a n x to the n plus b sum b n x to the n equals sum a n plus b n x to the n. You see, the wonderful thing about algebra is you don't have to worry about convergence, and so you just write it down. If you worry here about convergence, you're worrying actually about this horrible thing, limb sup or something. Here you don't have to worry about it. Second of all, the mapping F, G, well, no, let's call it P and Q. P and Q, you have 2 of these things. Formal power series. And this mapping is defined, is naturally defined. The word naturally is not a very good word. I just mean intuitively inside our classroom here, the word naturally. I mean that anybody who would think of this would think of the right definition, right? So if P is equal to sum a n x n and Q is equal to the sum bm, and here's where you need to learn to work with coefficients, as physicists know very well. Bm, then P times Q equals sum, let's say sum over k, n plus m equals k. A n b n x You get it? Right. Because you have to pick, it has to add up, you look at the coefficient of the x to the k, right? And that means you have to pick out something from the first and something from the second, then multiply it together to give that coefficient, so that's the condition, right? This is called Cauchy's formula. So this thing is an algebra because it has all these two operations and they're very compatible, and it's a wonderful thing. Okay. Okay. Now, now we have something else. We have the point 0, and we let O sub 0 equal, and now I'm going to say roughly speaking, the functions which are holomorphic near 0. Functions which are holomorphic near 0. Okay. Now wait a minute. The question is, what does this near mean? So here is 0. And you have some holomorphic function that's on U. So we have, here's a set U. Yeah? And you have F holomorphic on U. And that's certainly near 0. And then you have another set here, V. And you have another function here, say a G holomorphic on V. Now, those are two different functions because they have two different domains of definition. I've been talking to high school kids lately. A function has a domain of definition, right? And so holomorphic on a function holomorphic on U and a function holomorphic on V are two different functions, right? Because they have two different domains of definition, right? But these U and V intersect some way here like this. Okay? And we say that U and V, that the F and G are equivalent at 0, if and only if the restriction from U to V of F is equal to the restriction of U to V of G. Okay, so I'm being very pedantic here about what that means. R, U, V means restriction from U to V. Okay. Yes.
It doesn't matter whether we say restriction from U to V or V to U.
Yes. Oh, I'm sorry. No, I'm sorry. No. No. Well, no, you're absolutely right. Of course, you understand and ask a very good question. if the restriction from U to U intersect V, from V to U intersect V. Now you were happy? I'm sorry, I'm very tired, right? The restriction to this guy, this thing in the middle here that I drew, right? Let me emphasize, I'm terribly sorry. That's that guy in the middle. Two things are the same if they restrict it to the intersection, right? Okay. And an equivalence class of this equivalence relation, so equivalence class of F, say, is called the germ of F at 0. So germ in the sense it's very small, because you don't know where it's defined. Okay. For holomorphic things, it's not so dramatic, but for example, something that you might think about here is here's something C infinity, here's some function here, and this might be, here is maybe U intersect V, maybe with color. Yeah, here's U intersect V, and then here is the red function or pink function that goes completely bananas here, all sorts of bananas, and this is, say, U, yeah, and then a bluish function is the same here. They're going to be the same here, but it goes completely bananas out here for V. Okay. So it localizes at a point, yes.
Is it really an equivalence relation?
What?
Is it really an equivalence
Yeah.
relation? Because we might take like a third function that intersects with V, but doesn't intersect with U. Does then everything still work out? Because then, I mean, it might not even be defined on the any
It's
intersection.
trivially, if the intersection is empty, then it's trivially.
Let's see here. So if you have a third function where it's defined on W, so H holomorphic on W, okay. So I tried to be a little, I think you're right. I think
No,
you're,
I mean, I think pointed out that it might be trivially true because if you have no points to which you can compare it.
But 0 has to be in the intersection because we're looking at the jump at 0. So there always has to be
everything is at 0.
Okay, so you always require that it defines.
Yeah, but I think I was trying to make a shorthand notation here, and I think it's very much better if we define it the following way. They're equivalent if and only if there exists W in U intersect V such that this is what, and W, of course, is a neighborhood of 0. Yeah. I'm not sure it's exactly the same thing. I really mean this. Right? The restriction from some W, I don't care which it is. Okay? And then if you have, well, I had a W here, that's very bad. UV, I don't know, R. Now, this is what Nico's talking about. He's worried about this sort of thing, right? Right. And now, if we have U, V, and R, I just make sure that I'm in the intersection of all three.
Okay.
And then the transitivity of the equivalence relation is okay, right?
So it doesn't have to be the whole intersection, just...
No, and then, no. Yeah. Okay. Okay, so this is a way of localizing functions at a point. Okay. And so we get the space of equivalency classes, this thing, And if you have a function in this here, equivalence class, then the following map is well defined. I send it to its power series development. Right? Okay. I fix the coordinate, and then this map, which I'm going to call iota or I, is well defined. Right? So it says, after I've localized everything at a point, we have a map of these germs, of the localized functions at a point, using the coordinate, and they have a unique power series. This is embedded in, by what I'm calling iota, in the formal algebra, in the algebra formal power series in X. Okay? So we go from analysis to algebra, exactly here. Okay? The homomorphic function's in the neighborhood of 0, but localized. I'm only looking at 0. I don't care how far out they are. And each one has a power series, and associated to each one of these things is its power series. It's a well-defined map. It doesn't depend on the equivalence class, right? Because they agree in some neighborhood. And once I have this power series, I go to this. And now the theorem is, which we just proved, is the image of this mapping is the set rho bigger than 0. Right? Okay. And the fact is that this is an algebra morphism. So this means that I of f g, the formal power series of the product of two homomorphic functions, is the product of the formal power series. You need to check that. That's the key fact. Now Nico's looking mystified by it. Yeah, it's okay. It's good.
Excuse me, a question. So in this theorem, you say the image of the map which maps to the formal power series is the set of already? Or is it the set of all?
That's my notation. This is a set of formal power series, x, k, and it's such a row of the formal power series is possible.
Given some coordinate.
Yeah, and
But I guess it doesn't matter because if it's positive.
well,
then-
no, let's just say, let's just emphasize that this depends on the coordinate also, right?
I mean, should it though?
Yeah.
Because if you have some form power series, it can be mapped to a different power series for different coordinates.
That's right.
But I guess they should have the same
And
coordinates.
no, but if the thing is, if we use the coordinate 2z here for the power series development of a homomorphic function, it's going to be a different power series development. I mean, it's that. I'll just make sure you understand. I'll write it here. I use a different coordinate than the 2z, and I get different coefficients.
And that means we have a different.
And that means a
form.
different row.
Okay.
So this whole thing depends on the embed. Okay. Okay, that's a very interesting thing. And I recommend you don't forget it. Because you need to remember where you are. I mean, we're talking about really function theory, holomorphic functions here. We're talking about formal power series here. And the fact that this mapping is an algebra mapping is extremely useful. Okay? Because here, you can close your eyes and do anything you want. Right? There is no question, right? Here, there's no question about what you can do. So, to summarize this very inefficient lecture so far, I have a few more minutes.
Quick question.
Yeah.
So O0 is a quotient of all holomorphic functions by this relation, right?
Yes, yes.
Okay. And it's also a C algebra. It's also a complex algebra.
That's right, because the product of two holomorphic functions is holomorphic. That's, I'm glad Abik mentioned this, because in the back of my head, I have all this stuff without saying, I didn't say it. What is multiplication here and what is multiplication here? Multiplication here is formal multiplication. Multiplication here is just multiplication of functions. Right? And it says it's the same thing. Okay? It says it's the same thing. That's a good statement.
It also means that that actually is an injection that the dimension of O as a vector space has to be at most countable.
Both dimensions are countable.
I mean, it's clear that the dimension of the formal power series is countable, but it's
Oh, I
also-
see what you're saying. That's, yes, he is a very interesting remark. This thing has a certain dimension. I mean, here's a basis for it, right? These AKs. So you can count the bases, A1, A2, and so on. And then this is a subspace. This is very interesting. This is a subspace of a countable dimensional vector space. Is countable dimension. That's close. Is that close to a theorem or not?
Is it really countable because we are taking infinite linear combination, right? But basis only allows us to take finite linear combinations. So
What?
I'm
I'm not even sure this makes sense what we just said.
I think it is not countable, the basis. The basis.
What is the basis?
Yeah, right. I mean, what is the
This
basis?
is right. So that's the big advantage. I mean, you both hit on very good advantage. So the formal power series, the base is stupid. It's just these monomials, x to the k. Right? That's in some sense.
But that only gives us the
That's
basis
not a
for
basis either.
polynomials.
No, that's right. That's not a basis of a vector space.
Yes.
Right? Because if it were a basis, it would mean that every element is a finite linear combination of these elements. So what you're talking about is very non-trivial, right?
Right.
I think neither space is a countable dimension. Yeah. I think neither space is a countable dimension. Okay. So it's what I think Rabbi said. Here of course we have polynomials, which is something we understand very, very well. But that's not anywhere close to this thing. Yeah.
But didn't we say that we have that the formal power series is represented by the vector a 0 to a infinity? Something
That's
like
right.
that? So
Okay.
it doesn't give data basis? Or what is it?
Yeah.
Linear combination Prohan's point is still valid, right? Because if it's a basis, then the linear combinations have to be finite.
That's the thing that one always forgets.
Okay.
The linear combinations in this basis business, in algebra, are finite.
Oh, okay. So not.
So I have to, if we are claiming that this thing is finite dimensional, we have, or it has a basis.
It's not countable.
Yeah. I don't think so. I don't think it's countable. Anyway, I've not thought of it, this, I've thought a lot about this thing here, of course, and this is certainly not kind.
Oh.
Okay. Now, I have a few minutes, I would like to say something. In an algebra, you talk about units. So, the units in the formal power series, some algebra, these are the set of, let me call them formal power series, P, such that there exists a Q, such that P times Q is 1. 1 is in here. Okay, so the invertible elements. Okay. Do you know how to invert an element in the formal power series? I suggest this. I suggest a lemma. So a power series formal sum a k x to the k is a unit. Any suggestions? What's value? You want to look at 1 over this thing?
The first element is 1. Or is non-zero.
I would hope so.
Yeah.
I would hope that this is a lemma. That's what you said, right? Right. And my suggestion of a proof is 1 over 1 plus something. I'm going to write here, I don't know. I'm going to change P, okay, to that. All I have to do is, if A0 is not 0, then all I have to do is worry about the case A0 equals 1. Right, just factor out A0. And of course, this is this. Right? Isn't that the geometric series? And now what does it mean, this equality? It means, what does it mean, all this stuff? This is what I'm saying, this is going to be 1 over P, so it has to be a formal power series. And that means to compute what I've got here, I only am allowed finitely many operations. You understand what I'm saying? I'm not allowed to talk about convergence. Do you understand? There's a major problem here, what this means. Because, you see what I'm saying? This will always involve some form of convergence. But this involves 0 forms of convergence, because this thing, P hat, starts in it vanishes in some order, I don't know what it is. It's x to the k times something high order. So these, you don't understand what's going on here. The contributions here are only finite to each term in the formal power series. Do you get it? Right? So this inverts that. Okay. And then the units in the image of the convergent power series equal the convergent power series, which are units. Okay, so that's how, yeah? Because this thing is, if this thing is convergent, then this thing will be convergent. Okay? You check it. Okay? So you start to see that you have this thing embedded in this thing, and the algebra structure here is extremely compatible with the algebra structure here. product of two functions here is equivalent to the formal product of the two functions here. If the thing is a unit here, computing its unit is the same as computing it in the formal power series ring. It doesn't matter. Okay? So the question is, what can you do here and here the same? And I warned you, one thing you cannot do is X. Okay? So X, so if, try to make some sense, if you have a formal power series here, what does it mean, X? It almost makes sense in my mind. Okay? It almost makes sense. You understand what is X? X of sum AK x to k equals 1 plus sum AK x to the k plus sum AK x to k squared over 2 factorial plus sum AK xk m factorial and so on. Right. Now there's absolutely no problem for an analyst to do this because you just figure out what each coefficient is, right? So what this thing is 1, the first order term here is well, I'll just write it down. A0 plus A0 squared over 2 factorial plus and so on. Right? That's going to be the first term of the formal power series. But this sum does not make sense in the power series ring. Right? The only thing, this is what we're talking about, the only thing that makes sense in that is finite products and sums. If you take e to something like this, it doesn't make sense. Okay? Okay. So why do I want to take e to something like this? E to something, or any power function. The key is taking a formal power series and taking its root. Now, that's an algebraic operation. And if you want to define this in the usual way that analysts define this thing, yeah, you were forced somehow to do this. Yeah? But now watch. I'm going to quit in just a minute. But log of 1 plus p is exactly, you should never take log of p, right? Because it doesn't make sense because p, p is as above here. This, what is this thing? It's this alternating series that I just had, right? I don't know whether I just had it. Right? Right? Isn't that log? You should know log. Okay, and if p starts with a term x, or x squared or something, this thing makes sense. So log of 1 plus p makes sense. Okay? So this makes sense. And now this makes sense. Because this thing starts in p. And if we don't have any constant term here, this is not here. And then the contributions on the higher order thing are not related to any kind of convergence. Okay? So, in fact, fact, you can take roots by some way of cheating. I challenge you to have some fun. If suppose, yeah, okay, just compute, say, the root of 1 plus p to the n. Where p is this thing. You ever thought about that? I know you want to know.
Yeah, sorry, we have a lecture after that.
Yeah, I'm sorry, yeah. Yeah, I'm sure it's
So
important.
P is what power series exactly? Does n?
So you should go, you need to get to a lecture.
No, wait, all, yeah.
Here?
No.
Oh, yeah, okay,
No.
go.
So,
You should, I recommend that you compute in this formal power series, right? Particularly you computer science guys, because this is really,
so what exactly was P? Which power series was P? Or is this any power series?
no, I'm saying the log of 1 plus something, you know how to compute.
Okay.
That's it.
Yeah.
That's just a symbol,
Mm-hmm.
okay? Now, every formal power series is, again, you better not have log of 0. You're in trouble. So everything you're taking a log of is of the form up to a constant, 1 plus something, and this something starts with x or something like this.
Okay.
Right? And then you put that something in here, and you see that the right-hand side of this makes sense in the formal power series ring. Why does it make sense? Every calculation of you do some calculation, bm x to the n. You guys are much better than I am at this stuff. That means you've got to figure out what is the coefficient of x to the n. Every time you figure out what is the coefficient, you only do finitely many calculations. Okay. However, if it's an arbitrary thing with x, or log or something, you do infinitely many calculations. This is not allowed in the formal power series ring. There's a difference between analysis and algebra. Okay, thanks. I'll see you tomorrow. This is the lecture is a little bit for you.